Today, we're going to dive into one of the most fundamental and kind of hidden challenges in all of modern computing. It's a dilemma that quietly affects everything you do, from your quickest web search all the way up to the massive data centers that power our entire digital world.
So let's kick things off with this really key insight from Google. What they're saying is that our most powerful servers are basically like high-performance race cars. They're amazing when they're going full throttle on the racetrack. But in the real world, most of the time, they're just sitting there, engine running, burning fuel, and going absolutely nowhere. And that is the inefficiency we're going to talk about. And just how inefficient are we talking? Well, to guarantee those lightning-fast response times we all expect, servers in some of the world's biggest data centers often run at just 5 to 20% of their total capacity. I mean, just think about that for a second. Up to 95% of their computing power is just waiting, ready to pounce in an instant. So what's causing this staggering inefficiency? Well, it all comes down to a problem that engineers have nicknamed the killer microseconds. We're talking about tiny, almost unimaginably small delays, millions of a second, that when they start to add up, can absolutely cripple the performance of an entire system. All right, here's our game plan. First, we're going to really define this killer microsecond problem. Then we'll get into the two classic and competing ways of dealing with it. We'll see how this plays out in the real world with networking and databases. Then we'll look at the real cost of all this waiting around. And finally, we'll check out the super clever adaptive solutions that are changing the game. So what is this problem we're trying to solve, really? Well, at its very heart, it's all about a simple yet absolutely critical decision a computer has to make thousands of times a second. How does it know when new work has arrived, and when should it actually start doing it? To answer that question, a computer system basically has two fundamental strategies it can use. You can think of them as two totally opposing schools of thought on how to get things done. On one hand, you've got polling. This is like your impatient friend who's constantly asking, is it here yet? Is it here yet? How about now? It's great because the second something arrives, you know about it. The delay or latency is super low. But man, it is exhausting and wastes a ton of energy in CPU cycles. And on the other hand, you have interrupts. This is the patient friend who just says, hey, just wake me up when it gets here. This is incredibly efficient, uses very little CPU and energy, but there's a delay. There's a wake-up time that introduces its own latency.
And this right here, this is the dilemma. For decades, system designers have been stuck on this seesaw, forced to make a really tough choice. Do you burn an incredible amount of energy just to be fast, or do you sacrifice that precious speed to be more efficient? There was really no easy middle ground. Okay, let's make this real. Let's see this trade-off in action with our first case study, high-speed networking, a world where every single microsecond is absolutely priceless.
So there's this technology called Remote Direct Memory Access, or RDMA, and it's a total game changer. It lets one computer grab data directly from another computer's memory in a mind-bogglingly fast 1.6 microseconds. But here's the kicker. The traditional energy-saving interrupt system takes up to 10 microseconds just to wake the processor up. That incredible speed advantage is completely wiped out by the slow wake-up call. And if you're wondering why it's so slow, this diagram tells the whole story. An interrupt doesn't take a direct path. The signal has to go from the network card to a driver. It gets put in a queue. It gets handled by a scheduler. It might even have to wake up a totally different processor core. Every single one of these steps adds a few more of those killer microseconds to the total. So how do you fix this? Well, researchers developed this really clever hybrid system called FastWake. For the applications that need the absolute lowest latency, it uses our impatient friend, a dedicated polling thread that just completely bypasses that slow interrupt system. For everything else, it creates a much smarter, faster express lane for the interrupt, making sure that wake-up call goes directly to the right processor and avoids that long, winding journey we just saw. Okay, so we've seen it in networking, but this problem of waiting pops up everywhere. Let's look at a totally different world, databases. Now, the challenge here isn't just about waiting for data coming in from the outside. It's about juggling all the tasks that are already inside the system. So imagine a database is chugging along, running a long, heavy report for analytics. But suddenly, an urgent, high-priority sales transaction comes in. You can't just let it wait for that long report to finish. The solution here is pretty slick. A system called PreemptDB uses a special kind of interrupt that's almost like a manager tapping a busy worker on the shoulder. When that high-priority task shows up, the system sends a signal that says, "Hey, pause what you're doing for a sec." The worker immediately jumps on the urgent new task, and only when that's done does it go back to the original, lower-priority job. It basically lets the important stuff cut right to the front of the line.
So whether we're waiting for a network packet or for a busy processor to free up, the bottom line is exactly the same. These tiny, tiny microseconds of delay have massive real-world consequences. This chart really puts the cost into perspective. The fastest possible response, using polling, is our baseline at 1.6 microseconds. Now, if you use an interrupt to wake up a task on the very same processor core, you're already looking at 5.7 microseconds. That's over 3 times slower. And if that interrupt has to wake up a task on a different core, the latency balloons to over 10 microseconds. That is a whopping 6x penalty just for the wake-up call. And this brings us right back to the beginning. This is exactly why we see that 5 to 20% utilization rate we talked about. To avoid that huge interrupt penalty, data centers often choose the brute force option. They just keep their processors awake and waiting, polling, which, as we now know, is incredibly wasteful from an energy perspective. So if polling is a gas guzzler and interrupts are slow, where do we go from here? Well, the future isn't about picking a side. It's about being adaptive and getting the best of both worlds. You see, the smartest new systems are all adaptive. FastWeek chooses the right tool for the job, our impatient friend, polling, for some tasks, and a faster interrupt for others. PreemptDB uses interrupts to let important tasks cut in line. And other systems are even more clever. They act like a cautious friend who checks, is it here yet? More often when things get busy and way less often when it's quiet. They're dynamically blending speed and efficiency. This leaves us with a final thought. We've just taken a deep dive into one of the core trade-offs that has defined computing for decades. But as our technology keeps accelerating, new dilemmas are guaranteed to pop up. So the real question is, what's going to be the next killer microsecond problem? And what kind of ingenious solutions will it inspire? Thanks for watching.